Please take a look at the foundations of a modern bridge. How are such gigantic foundations built, especially when they stand on long concrete piles? Remember, the foundation is half submerged. To construct the foundation, engineers first need to install a watertight chamber, a caisson. Let's observe the installation of this massive structure. Can you spot a major issue in this installation? Water enters through the pile caisson joints, and the entire caisson is flooded. Think of a solution here.
The engineer simply extended few pipes outside the caisson. Now when they insert the caisson, the leaked water will stay inside these pipes and the workers can easily do the foundation work in the dry area of the caisson.
The long concrete piles we saw at the beginning, in fact, do not stop at the ocean bed. These long concrete piles travel through the ocean bed and extend even past the hard strata. They were constructed by pouring concrete into these steel casings. The big question is, how do you erect such a lengthy casing? No crane in the world can accomplish this task alone. Engineers used a crane and vibrohammer together to accomplish this almost impossible-looking task. The crane first carefully positions a steel casing as shown. Now, here comes the vibrohammer. If you look closely, you can see this machine is vibrating intensely, but with low amplitude. The vibrohammer pushes the hollow casing into the ocean bed. The vibrations of the casing make the piling process much easier. Now, the crane carefully places the next casing above the previous one. They get locked together. The vibrohammer, holding onto the second casing, starts driving. Once the second steel casing is also fully inserted, a third casing is connected to it. This time, the casing cannot go much farther down. It has hit the hard strata. However, the engineers want the concrete pile to extend below the hard strata as well. How do they do it? They first remove the soil inside the casing using an auger. Now a powerful machine called a cluster hammer begins its operation. Look at this drill bit with powerful teeth. The interesting thing about this machine is that the drill bit rotates and simultaneously performs a hammering action. This helps the drill bit break and pulverize the rock below. Here's the challenge. How do you remove the resulting debris? This is why compressed air is used. The compressed air passes through this narrow tube and finally reaches the teeth of the drill bit. The rock particles formed after hammering move along with the compressed air and reach this hollow central shaft. Finally, all the debris is safely collected in this box. Now everything is clear for concreting. This long cavity, which starts from the hard strata and extends even above the ocean surface, is filled with rebar. Such long pile holes are generally concreted using the Tremie method. This way, air gaps in the concrete mixture can be avoided. Did you notice something strange in the concreting? They never fill the concrete into the last steel casing section. We'll learn the reason for this later. Many such piles are erected on the ocean bed. Now it's time to introduce the biggest steel structure of this project, the caisson. We've already seen the details of caisson erection and the importance of these protruding casings. The first step before caisson insertion is to remove the last sections of steel casing we erected. This is why we didn't pour concrete inside them, for their easy removal. Now the caisson is slowly inserted onto the piles we've already erected. The watertight joints of the caisson will ensure that a sturdy platform is ready for the workers so they can start the main construction. The details of the rebar arrangement for the foundation concreting are shown here. Once the foundation is ready, the workers remove the caisson. For the concreting of such a long pier, engineers use an interesting technology called jump form. Here, the first concrete pour is done in a normal way. The forms that are attached now are mechanized. There are forms on all four sides. For simplicity, we're only showing one. Once the concrete has hardened, this interesting technology comes into action. With the help of this lever, workers first separate the form from the concrete. Now, look at this attachment below the forms. This is hydraulically powered. When the engineers activate it, the form starts its climb. In a few strokes, the form will cover the entire height of the hardened concrete. Now, the workers can close the forms onto the pier and start the next stage of concreting, and this cycle repeats. The pier is growing slowly and steadily. Why did the workers suddenly stop the concreting here? They're reducing the size of the pier. After the size reduction, the jump form concreting resumes. We'll find out the reason why they reduced the pylon size very soon. When the pylon is nearing its full height, the workers insert saddles. This is a crucial component for future cable installation. Now we've constructed one tower. For this bridge, the workers have to construct 3 more such towers. It's a magnificent sight to see all the towers standing strong in the water. They are waiting for the road deck to be installed. Before seeing that, first we need to understand how engineers know about the position of the hard strata and the length they had to drill. Before all these activities, they performed in situ soil testing. The project engineers had to conduct a detailed geotechnical study of the soil that will transfer a huge amount of load from the piles. They analyzed the seabed to ensure it would be able to carry the load of the permanent structure. The most commonly used test for measuring soil strength is an in situ test called a cone penetration test. You can see how the CPT device is placed on the ocean bed. The conical tip of the device penetrates the soil, and sensors send back friction and soil resistance values. Please observe how the soil resistance value changes as the cone penetrates. They will continue the penetration until they reach bedrock. You can see the sudden jump in the resistance value once bedrock is reached. With the help of this handy test, engineers know how deep the steel casing should be driven. Anyway, from here, we have to attach many concrete box girders and also make the cable connections to the main towers. These tall towers are waiting for that. Let's see the exciting phases remaining in the bridge construction. The construction of the very first box girder pieces is the most difficult task. For this, the workers first have to erect scaffolding like this. The first few box girders are constructed using the cast in situ technique. After this, workers prepare metal formwork with tight joints. Now it's time for concrete pouring. We'll soon see why these holes are needed inside the box girders. Once the girders have achieved this length, the remaining construction work is easier. After the box girders are cured, it's time to introduce the most important machine of this project, the segment lifter. The segment lifter is assembled piece by piece on the girder. Please take a look at these hydraulic strand jacks. These powerful machines lift the box girder segments slowly and steadily. Workers now apply epoxy glue to the surfaces of the girders. This plays a crucial role in bonding already cured girders together. These steel tendons are the invisible heroes in any concrete bridge. Workers insert the steel tendons from one end. They reach the other end, and with the help of this hydraulic jack, they tighten them. Remember, the steel tendons are locked at the other end. If cables are in tension, the concrete will automatically go into compression. This will increase the life of the concrete girders. Moreover, this operation will bond the different girder pieces together well. Let's install 3 more girders. Please observe the clever use of post-tensioning cables after each girder installation. Now, if you observe, we have created sufficient space to place one more segment lifter. The segment lifter for the left side. In the same way, the left side segment lifter also lifts and installs box girders. After a few steps, the left and right sides become perfectly symmetrical. Now begins the erection method called balanced cantilever construction. This construction activity is beautiful. the segment lifter lifting different girders, and the clever usage of post-tensioning wires, keeping them compressed. However, can you spot a major issue here? If we continue like this, after a particular length, this will happen. It's time to support the road deck from the main tower. From girder number 3 onward, the road deck needs support from the cables. Did you notice the hole they've included in the last box girder? This is intentional, and such holes will be present after every other girder. This steel piece, called the anchor, is first fitted into the hole. Please note, the angle of the anchor is important. Before installing the steel tendons, workers must first install HDPE pipes. Here, they're joining different pieces of HDPE pipes together by heating. First, the HDPE pipe is suspended in the air with the help of a crane. Now comes the use of the tendon pushing machine. This machine pushes the tendons one by one. The tendons reach the other end of the HDPE pipe. After that, they pass through the holes of the saddle. The tendon cables reach the other end of the saddle and travel through the HDPE pipe again. After a long journey, they eventually reach the other steel anchor. Here, the tendons are tightened with the help of a stressing jack. Now, the road deck is properly supported. The post-tension tendons are compressing them and bonding them together, and the cable support from the top gives them much-needed stability. Cable support is needed after every other girder. The way the road deck progresses looks beautiful. Even the other tower girder assembly progresses using the balanced cantilever construction method. Eventually, both the cantilevers meet in the middle. The last segment of the road deck is again fabricated using cast in situ techniques. This bridge, which is located in Goa, India, has a very gradual connection with the land. What we have just constructed is called a cable-stayed bridge. Driving across this bridge offers a blend of modern engineering and scenic beauty. Cable-stayed bridges have taken the civil engineering world by storm. Their popularity increased drastically after the 1950s. However, you may have seen a totally different type of cable-stayed bridge in your city. Here is one such bridge completed in 2009, with a total length of 5.6 kilometers. Look at the tower or pylon of this bridge. This kind of design is called a diamond pylon. Moreover, this bridge is not purely a cable-stayed bridge. It's a hybrid bridge. One portion of this bridge is cable-stayed, and the other portion is a normal beam bridge. Diamond pylon bridges have high geometrical stiffness. They're also aesthetically striking. In fact, cable-stayed bridges can have 5 major types of pylon designs based on the situation. The third pylon design is called the H-frame design. The H-frame consists of 2 vertical columns connected by a horizontal crossbeam near the top or middle. They offer good lateral stability and are ideal for bridges with balanced spans on either side. The Severensbrücke bridge in Germany is quite unique. This type of cable-stayed design is known as an A-frame design. This design transfers the load more efficiently to the base. Horizontal crossbeams are generally not needed for this design. This design may look similar to the A-frame design, but here the legs diverge downward from a single shaft, creating an inverted Y. The Guadiana International Bridge in Portugal follows this design. We've already seen the I-shaped cable-stayed design. Here, a single narrow vertical tower rises from the foundation. The I-shaped design is obviously the most minimalist one. This kind of cable arrangement is called a modified fan arrangement. There are 2 more ways to arrange the cables for a cable-stayed bridge. The other 2 designs are fan and harp arrangements. With all this knowledge we've accumulated now, let's understand the engineering behind the longest sea bridge in the world, the Hong Kong-Zhuhai-Macau Bridge. The The length of this sea crossing is a whopping 55 kilometers. This marvel of civil engineering features 4 artificial islands, 1 underwater tunnel, and 3 cable-stayed bridges. The longest section of the crossing is this roadway with a length of 29.6 kilometers. The 3 cable-stayed bridges are part of this long section. Then starts the underwater tunnel, 6.4 kilometers long. You can see 2 artificial islands at both ends of this tunnel. Now, the journey continues on a 12-kilometer elevated roadway. And eventually, we reach Hong Kong. Cable-stayed bridges are exploding in popularity. Even though cable-stayed bridges are typically meant for a span range of approximately 150 meters to 600 meters, nowadays, more and more cable-stayed bridges are being built with longer spans. For example, the longest span cable-stayed bridge in the world, the Russky Bridge in Russia, has a span of 1,104 meters. In contrast, suspension bridges offer much superior spans. The Golden Gate Bridge, which was built in 1937, has a span of 1,280 meters. Japan's popular Akashi Kaikyo Bridge has a span of nearly 2 kilometers. Despite their superior span, engineers today often prefer cable-stayed bridges over suspension bridges. The main reason for this is constructability. In suspension bridges, the main cable has to be laid completely before starting the hangar and road deck assembly. And to lay the main cable, one must wait for the construction of the main towers to be completed. Now, look at the construction sequence of a cable-stayed bridge. Even before the pylon construction is completed, engineers can start the road deck construction, and the laying of stay cables and road deck progress simultaneously. The second reason is the ease of maintenance. Suppose one of the main cables of a suspension bridge needs replacement. This is how engineers must proceed. First, a temporary structure with hydraulic jacks must be constructed under the main span. Once the main cable's load is transferred to the temporary structure, they can dismantle the main cable and repair it. If any cable has to be replaced in a cable-stayed bridge, it's a relatively simple task. The cable-stayed bridge has good redundancy. Without building any temporary structure, engineers can replace a cable. Another main reason why cable-stayed bridges have become super popular over the last few decades is the optimization of tension in each stay cable. The girders of a bridge experience bending moment due to the live load and self-weight of the bridge. Cable tensioning significantly reduces this bending moment. Due to the advent of accurate FEA models, engineers are now able to predict the optimum post-tensioning needed for each cable, allowing the girders to have a slender design without compromising their structural integrity. In fact, the competition between cable-stayed and suspension bridges is a story worth telling. The very first design that captured engineers' imaginations was the cable-stayed bridge design. Here is a theoretical design by Fausto Veranzio in the 16th century. When it became a reality in the 19th century, the design was met with terrible failures. One of the earlier cable-stayed bridges, the Dryburgh Abbey Bridge, collapsed in January 1818, just 6 months after its inauguration. The Saale River Bridge in Germany also met the same fate. It collapsed in 1824 when 300 soldiers marched across it. After these incidents, truss, arch, and suspension bridges became the popular bridge designs among engineers. When a bridge had to carry a heavy load, they opted for truss and arch designs. If the span requirement was too high, they opted for suspension bridges. This trend continued for nearly 130 years. Cable-stayed bridges were completely forgotten. In 1955, the German engineer Franz Dischinger breathed new life into cable-stayed technology with the Strömsund Bridge in Sweden. Franz Dischinger used a fan arrangement of cables instead of the old harp arrangement. He was able to calculate the force developed in each cable and determined the optimum angle for them. He also used pre-stressed concrete in this bridge. After the success of the Strömsund Bridge, cable-stayed bridges began to mushroom all across Europe and Asia. Finally, the U.S. also joined the trend with the inauguration of the Ed Hendler Bridge in 1978. Cable-stayed bridges have overshadowed suspension and arch bridges in popularity, but even now, when the span length requirement is extremely high, engineers' choice is always the suspension bridge. When engineers need exceptional structural strength, they still prefer arch bridges.
In all these bridge designs, you might have observed one thing. The foundation of the bridge is half submerged in the water. Why don't the engineers build the foundations like this? In this case, caissons are no longer needed for the construction. What an easy way to construct bridges. Please let me know in the comment section, why don't we build bridges like this? Anyway, it's almost impossible to believe that starting from such a simple design, we have reached such a sophisticated engineering less than 70 years. Construction of the bridges and their history. This was such a lengthy video. We are in fact struggling to produce such lengthy educational videos using Google AdSense revenue alone. So if you can support us on Patreon, that would be great help for me and my team. Hoping for your support. Take care. Bye bye.